Good afternoon, class. Today we'll be looking at section 3 of chapter 7. This is actually kind of a review to the last chapter. We're just going to be looking at very specific parts of it. The first concept, theorem 7.5, it doesn't have a name. It's kind of using what we already know, and it just says if an altitude is drawn to the hypotenuse of a right triangle, then the two triangles formed are similar to the original triangle and to each other. What that's basically saying is, if I take a right triangle, such as this one here, and I drew an altitude downward, the three triangles I see here, the triangle on the left, the triangle on the right, and the big triangle, are all similar. In the first example, I'll go over how to set it up, but that's all this theorem says, is that there's three similar triangles. On the screen, you'll see the big one with the altitude drawn in it, and you'll see the one that just takes the left part, and you see the one that just takes the right part. Those are the three triangles that are similar. In example 1, what I want us to do is that we take a triangle, and we're going to be saying the three triangles that are similar in it. So, first of all, redraw your triangle. In a problem like this, I always find that a visual aid helps. So what I'm going to do is, even after I redraw my original triangle, what I'm going to do is I'm going to draw three more triangles. One here, the one that's slightly smaller, and one that's slightly smaller yet. I'm going to make it so the right angle is down in the bottom left, and I'm going to make it so 1 and 2, 1 and 2, 1 and 2. Now, why did I put 1 and 2 there? It's just a little bit of help for me. Now, if I look at my original triangle, I have to line this up so it matches in. Usually what I do is I try to line up this triangle to the original. So this will be A, C, D, which means angle A is angle 1. So I'm going to put a 1 right here. That also means angle C is a 2. Now, the whole point I'm putting a 1 and a 2 here is so that way I get my letters here right. The big triangle is pretty easy. You just copy it down and you draw it again. Now, let's look at this triangle here. The one that looks slightly bigger to me. It's the one you should be able to see now. The right angle is B. The only angle I have marked is C over that, and that is angle 2. So over here I'm going to put C. The last angle of this triangle here is D. Now, why did I put that 2 there? So I could line this up easy. 1, 2, 3. I plug it in. I see where it goes. Angle 2 matches up. That angle C matches up to that angle C. Awesome. Now for the last triangle, I cover up the bottom half. The right angle is again B. So I'm covering up the bottom half. The only angle I have marked in this part of the triangle, so the upper left, is 1, and that's angle A. So I put A at 1. I'm looking at the top triangle. The last angle would be angle D down here. It's actually angle BDA, but D goes here. I now have my three triangles lined up with angle 1 being congruent to angle 1 being congruent to angle 1. Angle 2 being congruent to angle 2, which is congruent to angle 2. And all three right angles are in the bottom left. It's now lined up. If I want to identify the three similar triangles now I just make sure I go in order. Triangle, I'm going to start at the right angle. D, go to angle 1. A, and at angle 2. C is similar to triangle, right angle, angle 1, angle 2. Triangle BDC, which is similar to triangle, start at the right angle. B, go to 1. A, go to D, 2. D. So, triangle DAC is similar to triangle BDC, which is similar to triangle BAD. This, now, I could know which triangles are similar. If I wanted to, I could set up proportions. That's right. Chapter 7, Section 3 is a review of Chapter 6. Whenever I see similar, automatically I'm thinking proportions. However, in example 1, this is all they wanted. And this was made easier by drawing my three shapes and matching up angle 1 to angle 1 to angle 1. Now, angle 1 is D, and you might look at this and say, how is this angle 1? Well, for this triangle, remember, B was the right angle, C was angle 2, so by process of elimination, D had to be angle 1. That's how I figure this out, where to place the letters. But I'm going to draw 3 triangles, one big, one medium, one small, all facing the same way with 1 and 2 in the appropriate spot. There we go. Example 1, done. Example 2 will go a little bit faster. What if I gave you a problem that looked almost like this? It has, in fact, it has the same shape, but it says find the value of the variable. Round decimal answers to the nearest tenth. Well, again, I would redraw my shape. The full length over here is square root of 149, and this is 10, and I'm looking for this length right there. Well, I have my 3 triangles drawn, right? Well, similar triangles, I automatically know I'm going to be doing this. So I write down my proportion. I don't know which one I'm going to do yet, but I'm going to write it over there. Now, all 3 triangles in one shape. It's brutal. It's tough to do. Luckily, I used a triangle from one example ago, so I already have my 3 similar triangles drawn. If not, I would redraw them. Segment AD, do I know its length? Segment AD is 7. I filled in. Segment AC, A to C, square root of 149. Segment DC, I know that length, it's 10. Segment DB, I don't know that length, but that's the one I'm looking for, it's X. Segment DC, 10. Segment DC, segment DC. Segment BC, don't know it, leave it. Segment AB, don't know it, leave it. Segment AD, 7. Segment BD, that's what I'm looking for. Now I look, these 3 triangles are similar, and they're matched up so the corresponding sides are all on the left, corresponding sides are on the bottom, and corresponding sides are all the right hypotenuse. So I look. It doesn't matter which triangles I choose, as long as it's this triangle and this one, or it's this triangle and this one. If I do these 2, I don't have 2 corresponding sides to 2 corresponding sides. My choice, the first 2 triangles. I'm using this one and this one. I want to find X. X, its corresponding side is 7. X to 7. Now I went from X to 7, so I have to stay here. 10. So I went X to 7, I have to start with 10. To square root of 149. So X to 7, 10 to square root of 149. I have my proportion. Solve. 10 times 7 is 70. Square root of 149 is square root of 49x. Divide both sides by square root of 149. That's what I get. At this point, you're going to need a calculator because it said round answers to the nearest tenth. So you pull out your calculator, you hit 70, divide by, now the square root button. Most calculators is right above the square. You might have to hit second, the square button right there, and now it's the square root. You plug in the number, 149, close your parentheses, and you hit enter. And in this case, I ended up getting total answer of 5.7. There you go. So, when you're given a problem like this, you see an altitude in a right triangle. First step, redraw your 3 triangles. Second step, fill in what you know. Third step, set up your proportion. Fourth step, cross multiply and solve. That's it. So step 1, draw your 3 triangles. Step 2, fill in everything you know. Step 3, set up your proportion. Step 4, solve. Now, there's something called the geometric mean. This shape is actually where the geometric mean comes from. The 3 shapes that are geometric mean, the one that in my mind makes sense to me is segment CD. So in this case, it's the segment from the right angle to the opposite side. It's the altitude. The altitude of a right triangle is a geometric mean. In fact, it's what I would call the geometric mean of a shape. Segment CB also ends up being a geometric mean of something, and segment AC also ends up being a geometric mean. What do I mean by that? If I look at my shape here, and I set up a proportion using the 2 triangles on the left, what if I compare the right side to the bottom, BD to CD, and I did the same thing on the right, the middle triangle, CD to AD. I look, CD is in the upper right and bottom left. That's a geometric mean. That shape, segment CD, is a geometric mean of segment BD and segment AD, which if I look, it's the two parts of my hypotenuse. If I set up a proportion using the right two triangles, if I compare the bottom to the hypotenuse, bottom to hypotenuse of the middle triangle is AB to AC. The bottom to the hypotenuse of the bottom right triangle is AC to AB. And I look at the proportion I just set up. AC is a geometric mean. It's in the upper right, bottom left. And the last one that's a geometric mean is if I compare the left triangle and the right triangle. What if I compare hypotenuse to the right side? Hypotenuse to the right side. AB of the right triangle, BC of the right triangle. CB of the left triangle to DB of the right triangle, left triangle. So hypotenuse to right side. And these match up again. AB to CD, AB to CB, CB to DB. The CB is a geometric mean of AB and DB. If I look at where AB and DB is and where CB is, the leg of a triangle is a geometric mean of the part of the hypotenuse closest to it and the full hypotenuse. There's three different geometric means in a triangle. And that's what I can do here. Now, for this next part, all I'm going to ask you to do is fill in the remainder of the proportions. So if I look at this here again, I use the same shape. That was relatively nice. So I'm going to re-erase this. We have no side lengths. We aren't interested in side lengths right now. Now, if you remember which ones are geometric means, awesome. If you don't yet, that's fine. We'll discuss that more later. Let's take a look at it. I see this. I immediately draw three triangles. Big, medium, small. Right angle, right angle, right angle. One at the top, two in the bottom right, and I marked 1 and 2 here. Big triangle. A goes in upper or the top, D goes in the bottom, and C goes here. That's just a copy of my big triangle. Alright, next one. Both right angles of my small ones are B. So I'm just going to put B there now. So let's look at the top triangle here first. The right angle is B. Angle 1 for the top triangle is A. The last angle is D. I just made up this triangle here, right there. Alright, how about this triangle right here? B is my right angle. C is angle 2. D is the last angle. I have now set this up. Now what is this doing some comparisons? Alright, I look. Those are my three proportions I had. Now to tackle this, what I'm going to do is I'm going to find which triangle has both of these. A, B, and BD. So I look. Which one has A, B? Nope, not this one. A, B, and BD. Right here. Boom, boom, right there. Left to bottom. Left to bottom. Which one has a bottom of BC? So the ratio is left to bottom. Which one has a ratio, the side length of BC in the bottom? It's this one. So left to bottom, left to bottom. I need segment DB or BD. Let's try the next one. I don't know this ratio fully. However, the ratio on the right is AD to AC. So I'm going to look for which triangle has AD and AC in it. Alright, so let's just start with the big one. AD, AC, right here. AD, AC. Left to hypotenuse. Left to hypotenuse. I'm given the hypotenuse of AD. Hypotenuse of AD. So which one has the hypotenuse of AD? It's this one. So left to hypotenuse, left to hypotenuse. My segment has to be AB. Alright, let's try it for the third time. If I look, they give me a ratio BC to DC. So which triangle has BC to DC? BC to DC, bottom, hypotenuse. Which one has a bottom of DC? Right there. So bottom to hypotenuse, bottom to hypotenuse. I need AC right here. And that's how we do that. So if I'm looking for a proportion, match it up. Again, you're drawing 3 triangles. Which one does it fill? Alright, so we just got done setting up all these different ratios. Well, what we found out that there were some shortcuts depending on what I was looking for. The shortcuts are geometric means. So the shapes I said before, AC, DC, and BC, they're geometric means, which means I can set them up a certain way just by looking at it. Now the theorem says, in a right triangle, the altitude from the right angle to the hypotenuse divides the hypotenuse into 2 segments. Those segments in the picture you see there is segment AD and segment DB. The length of the altitude is the geometric mean of those 2 segments. So that means if I gave you lengths, you plug it in into the geometric mean. CD, bottom left, CD, upper right. You would put length of segment DB in one of the other 2 spots, and length of segment AD in the other one. That's how you would form your geometric mean. What do I mean by that? Well, let's look at an example. Find the value of the variable. Let's draw the picture. Now, I'm not going to put my letters in here. I could, but I'm not going to. I'm looking for x. I see that x is an altitude. Now, the theorem I just got done talking about was the geometric mean altitude theorem, which means I can set up a proportion just by looking at this. X is the altitude, which is the geometric mean of this portion and this portion, which means I put this portion, 3, in one of the 2 spots left open, and 10, the other portion, into the other spot. Now I look at my proportion here, and I'm like, hey, I can solve for x. X squared, x times x, equals 3 times 10, 30. Square root both sides. X is equal to the square root of 30. Now, I really can't make that any nicer than the square root of 30. Either leave that in simple theoretical form. If they ask for decimal, plug into your calculator. But look at this. We can now make shapes that would be square root of 30. And if I could calculate this, making this 2 and this 1 here, I could get the square root of 2. I could get the square root of 3, square root of 5. Geometrically, this shape, if this was drawn to scale, would be square root of 30. Perfectly, the square root of 30. Whoa, that's awesome. Alright? So, the geometric mean here, square root of 30. I made square root of 30 the exact length of it if I would have drawn it to scale. But there you go. That's how you set up a problem like this. The altitude is the geometric mean, xx, of 3 and 10, the 2 parts of the hypotenuse. That's all this theorem says. You need to know it. You need to be able to set it up. It saves time. Could I have done this problem the other way that I taught you before? Yeah, draw 3 triangles. Yeah, you can do this the old way. It's guaranteed to work. But if you know the shortcut, you save a whole bunch of time. This took another minute or 2. This took 30 seconds if I know the theorem. Alright, know the theorem. Altitude, geometric mean of these 2 parts. Alright, that being said, there's another geometric mean theorem. It's called the geometric mean leg theorem. In a right triangle, the altitude from the right angle to the hypotenuse divides the hypotenuse into 2 segments. That's still true. Okay, so in the picture, AD and DB are my 2 segments. The length of each leg of the right triangle is the geometric mean of the lengths of the hypotenuse and the segment of the hypotenuse that is adjacent to the leg. A lot of words, but what does that mean? Choose a leg of the original triangle, AC or CB. I choose CB. That is the geometric mean of. So as soon as I say geometric mean of, I put CB in the bottom left, CB in the upper right. That's the bottom left proportion right here, down here. CB, bottom left, upper right. It's the geometric mean of the hypotenuse. So I put the hypotenuse, AB. It doesn't matter, upper left, bottom right, but one of the 2 spots, I put in the upper left. And the segment of the hypotenuse that is adjacent to the leg. Adjacent, next to, right near, alright? that would be segment DB, because that's the one actually touching CB is segment DB, and it's only part of the hypotenuse. So that's how I got the bottom left proportion. Similarly, I would make the same argument with segment AC. I'm going to ask you to find all the variables. So I ended up using the same picture again, but we've changed the numbers. We're not going to do it the old way. We're only going to use the shortcuts here. So that means I'm going to erase the 1 and the 2. All right, awesome. So this is 2 here. This is 8. This is X. This is, oh, my bad, that's Z actually. Z, X, and Y. Now, the geometric means in my shape, I'm going to highlight in blue. There's this one here. There's this one here. There's this one here. All three of these end up being geometric means. It just so happened that my variables I chose here were geometric means. Are they always? Definitely not. But in this case, they are. I'm going to try to find X first. X is a leg of my original right triangle. So that means it's a geometric mean. If it's a geometric mean, I right away set up my proportion. X, bottom left, upper right. What is it the geometric mean of? Well, it's of the part of the hypotenuse closest to it. So the part of the hypotenuse closest to X here is 2. And I'm only looking for part of it, so I'm going to throw part of it up there. And the full hypotenuse from A to C. That's not just 2, it's not just 8, it's 10. So again, X, geometric mean. So I put it bottom left, upper right. 2 is the part closest to X of the hypotenuse. And remember, the hypotenuse is always across from the right angle. So 2 is the part closest. 10 is the full length, so I put it down there. At this point, it's just solve. X squared equals 20. X equals square root of 20, which if done correctly, I believe is X equals square root of 4 times the square root of 5, or X is 2 square root of 5. Alright, let's do the other leg right away. The other leg here is the bottom one, so that's Y. And geometric mean. It's a geometric mean. Awesome! So that means I can put Y in the bottom left and upper right. Yes! It's a geometric mean of the part of the hypotenuse closest. Part of the hypotenuse closest. Part of the hypotenuse closest to Y. Oh, that's 8. So put 8 in upper left or bottom right. It doesn't matter, but choose one. And the full hypotenuse. 2 plus 8 is 10. Got my proportion solved. Y squared equals 80. Y equals square root of 80. And I believe I can break this up into Y equals the square root of 16 times the square root of 5, or Y is 4 square root of 5. I found X, I found Y. Now it's time to find Z. Z is an altitude. Again, Z is the geometric mean. So let's throw that into the geometric mean. Bottom left, upper right. Yes! The altitude was the geometric mean of the parts of the hypotenuse. Oh, so I don't even have to worry about the full hypotenuse or which one's closest to Z. It's just the parts. The parts of the hypotenuse is 2 and 8. So I put 2 in one, I put 8 in the other. Z squared equals 16. So Z is 4. And there we go. If you cannot remember the geometric mean theorem, what you have to do is you draw 3 triangles, 3 different sizes, big, medium, small. You line them up and put everything that you know in. Then you find the 2 that are similar that will help you out, and you make your proportion. Once you make your proportion, you solve. If you know the theorems and you can set these up without drawing the 3 triangles, that's awesome, that's great, do it that way. But if you can't, draw the 3 triangles and review chapter 6, because that's just setting up the proportion from 2 similar triangles. This chapter is a little bit tough. It is a tougher one because you have to set up the proportions. It's kind of a standalone section in this chapter. Do your best in it. Otherwise, till next time.